Hi, Brent. Today we're going to go over a couple of things I learned from exam PA. So the first thing is that there's there is some calculations that are going to be involved in the entire exam, but it's more dependent upon really just in general, like your GLMs, EDA, and like clustering algorithms, like clustering, that's something that could be asked for you to actually do the calculations on, the GLM's EDA, and like even like a lot of like the nuanced, more detailed portions of these topics can also be asked. So, for example, for GLMs, things like weights, or for linear regression, things like offsets. So a lot of these other like side topics related to these main topics that you also want to make sure that you have in mind. Some of the things that you don't want to make sure is, or you don't. It's fine if you don't really memorize it, or some of like the very the very long formulas, so like the formula for deviance, or like formula for chi-squared stat, or the formula for the I believe a Gini index you might need, an entropy you might need, but if it's like some weird like or very long formula, you're probably not going to have to need it during the actual exam because exam is very conceptual and it's going to focus on these high level topics more so than the calculations. You might have to do some, but that's mainly focused on clustering, EDA, generalized linear models, and things like that. Also want to be pretty good on like a reading R output, especially when you have like GLM output or linear regression output. You want to be comfortable with that. Additionally, like let's just go over a couple of things. So for random forest, let's go over random forest versus linear regression. So a couple of things to know about random forest is one of the things about random forest is that it has many decision trees, right? Decision tree is just one single decision tree. Random forest, we have multiple decision trees, and now how do we actually get these multiple decision trees? Well, first we have the entire concept of creating bootstrap samples. And what does bootstrap samples mean? Let's say we have our data set over here, and we are, let's say it's 10 observations, 10 observations. We created our decision tree, our one decision tree from these 10 observations. Now what we're going to do is we're going to randomly sample 10 observations from this original data set. So now allowing for duplicates, so we're going to be sampling with with replacements. So we're going to allow for duplicates, and we're going to build another decision tree. We're going to build another decision as a decision tree, but this time we're only going to use a subset of the variables. So if we have, let's say, 5 variables, we might randomly select that we want 2 variables in this decision tree, and then we make another decision tree from the bootstrap sample from the 10 observations in our original data set. And we have another data set. Let's say we're going to have 3 variables, and we have another decision tree. So in this case, in this random forest example, we make continuously keep on making decision trees until we reach like the maximum of trees or some other hyperparameter. And so one of the reasons that this actually works is this helps reduce a lot of the overfitting that occurs for decision trees. Because in decision trees, one of the disadvantages that you can have in decision trees is you can just have this very large tree that's going to be very overfit to your training data. One of the ways you can combat that is by having multiple different decision trees trained on really different like versions of the data as well as different variables because you're randomly selecting which variables you want when you're building the tree itself. And so that is able to really reduce a lot of the overfitting that occurs, and it's able to generalize well to a new unseen data point. And so that's one of the benefits of random forest. Another thing, it captures nonlinear relationships really well compared to obviously generalized linear models. It's also very robust to outliers. So in the case of linear regression or GLMs, they're very sensitive to outliers. Random forest, it it's able to deal with those outliers in a very coherent manner. So deals very robust to outliers. Random forest also has interaction terms, and these are part of the actual model itself. And one of the nice things about random forest is it provides a nice visual for the model. So it's very interpretable. You can literally like you can have a visual, even if it's like with 4 or 5 different dimensions or even more, you can have a visual where you draw the tree diagram where you can see, okay, if this variable is this, then we go left or right. It's very, the ease of explanation is very apparent with random forest as compared to when you have like, let's say 6 variables in a linear regression model, it's very difficult to actually visualize that. The visualization is one of the key advantages of random forest. So that's that, and then we talk about clustering a bit. So we have k-means clustering. So how does k-means clustering work? K-mean clustering works by first we randomly initialize. So first, obviously, we need a k value. We need to know the number of clusters. We first randomly initialize. Let's say k equals 3, just as an example for the process of how to understand this. So let's say k equals 3. We're going to have k 3 clusters in our data set. First, we randomly initialize 3 centroids in our data set. So you can put them just anywhere that you want in data set. And now we assign each of the points to the closest centroid. Assign each point to closest centroid. And then what we do is we recalculate the centroid. Because now we have new points for each centroid or for each cluster, and now we can recalculate the centroid. After we recalculate the centroid, we then reassign the points based upon the closest centroid. And we keep on doing this until we reach a convergence such that there are no such that in 2 consecutive iterations of this, the clusterings don't actually change. All of the points stay with their respective clusters, and that's when we know that we are able to stop this k-means clustering algorithm. One of the drawbacks of k-means clustering is because of this initial randomization portion. Every iteration, unless you have a random state, you might get a different clustering result. So not always, but it is certainly a possibility that you get a different clustering result if you run k-means more than once because of this random process when we're initializing the centroids in the beginning. On the other hand, when we look at dendrograms, when we look at hierarchical clustering, there's no process of randomization. We start with each individual point being its own cluster. We calculate dissimilarities, and we're able to merge. We're able to merge different data points together, and we're able to create sort of merge clusters and sort of have that bottom up approach. There's no randomization that's involved as we see in k-means clustering. So if we run higher clustering multiple times on the same data set, we're going to get the same clustering, the same merge clusters, whereas that may not be the case in k-means clustering. And then another thing to go over is k-means clustering is also very sensitive to outliers. And we always want to make sure that before k-means clustering, before really almost all clustering algorithms, we want to make sure that the data is very standardized. Because if it's not standardized and we have these large variances in terms of the scale of the variables, that can have an effect on the Euclidean distances that we're actually minimizing. And if it's a large scale variable, that may have a larger distance than what you want to actually have in the clustering. So in order to make sure that all of the variables are represented equally and no such variable has a greater significance in the clustering, which we can talk about like how there's ongoing research and this is another topic. How can we add actual weights to our clusters where certain points are actually weighted or certain variables are actually weighted more significantly? But in this sort of generic case of k-means clustering, we want to make sure that our variables are standardized, that we're subtracted by the mean divided by the standard deviation, so that they're not influenced by the large differences in the scales of these different variables. And so that's k-means clustering. One of the things, let's see, a PCA. PCA is a very good tool for data visualization, especially if you have many different dimensions. So first dimensionality reduction, if you have, say, 1,000 data points and you want to condense that into like two or three, really getting the core of what the variance in the data set is, you can use principal component analysis to reduce the number of dimensions. One of the things is sometimes it may not be that interpretable. Yeah, you can interpret the loadings and from what variables and the weights of the variables that are in each principal component. But if you have like a very interpretable data set where you have every single feature, and then you want to go back and try to semantically derive like the meaning behind the piece principal component analysis that's formed, it probably is going to be a bit difficult in that regard. And so that's one of the cons is it does have some interpretability issues, but it is a great tool for data visualization, obviously great tool for dimensionality reduction. It's a great tool for if you have, let's say, correlated features in your data set. If you have correlated features in your data set, one of the things about PCA is that all of the principal components are actually uncorrelated. So if you have a correlated data set, and let's say you want to plug that into a model, that's going to have very high collinearity. It's not going to produce optimal results. But you can use PCA to convert that into something that's not something that's independent. All of the principal components are independent of one another, so you can use that for model building purposes. A couple of other things that I'd like to go over. So in addition to, so let's talk about decision trees. We talked about they're very prone to overfitting, which is why we have random forests in the first place. They actually have a lower predictive accuracy than random forests. They're highly sensitive to the training data, and they're obviously greedy algorithms. They're greedy approaches. So they're very unlikely to produce the global optimal model because they're looking only at the next best split that could be taken. One of the advantages of decision trees is that obviously they're robust to outliers. They're good at recognizing nonlinear relationships. They're easy to interpret and have good visualizations in terms of the tree diagram. There's no assumptions that need to be made about the data or that you know about the data. So if you just encounter the data set, you don't know like what the underlying distributions or what how the data was collected. If the certainty of the data is not apparent, you can use decision trees. And let's see, there's also a couple other things. So we have competitor splits as well. So when we're doing splits and decision trees, we get like the single best split that has the highest reduction in SSE, but there could also be competitor splits which are similar to the best split, but we just want to make sure that, hey, A, note that there are other splits that are similar to the best split. They're pretty close. And so that yields good information in the sense that, hey, if we know that there are actually other splits that are pretty competitive, that may lead insight into like some variables, or it's just a very, very good information to have. And then we also have these are the other four or five variables that were had a strong reduction in SSE compared to this variable as well. So it just helps to understand like was this best split by a large margin, or were there other variables that were close as well? And let's see. So another thing is boosting. So bagging refers to the fact that after we've done uh, we've we've done our bootstrap and we have built our decision trees, aggregating all of the predictions. If it's classification, finding the majority vote. If it's a regression problem, finding the average of the predictions, aggregating them. That's what we call boosting. Um, or I think that was not boosting, bagging, right? Bagging. So it's bootstrap aggregation or bagging. And then boosting is where we predict the response variable, and then we also predict the residuals, and then we predict the residuals of those, predict the residuals of those. And so this one of the parameters here is actually learning rate that you can incorporate into the model for boosting. So that's another one thing to note. And ultimately, I think that's about it. Go over a few NFL plays here. So we have official play is Rams money line. And then, so this is the official one. The reason behind this is because Raiders had just upset 325, I think Browns, and very, very rare for a team to do 325 upsets in the same season. So official pick is Rams money line, and then so sort of like the leans, not official pick, but things I'm leaning towards Jets money line. Again, it's only been two Sundays from the Sunday Night Football upset. And then we have Jets money line. We have Ravens money line is because of the fact that Lamar Jackson versus NFC teams, as well as there was one more that I think I actually like. So there was Rams money line, Jets money line, Ravens money line. I believe there was one more that I actually really like, but for now we'll stick with this. Okay. Okay, I think that's it. Yeah, I think that's it. So exam PA, just remember, like, you don't focus too much on the formulas. Yeah, there's maybe some clustering things, formulas you may need to know, but really focus on the big picture concepts and really even just take a practice exam just to get familiar with the environment. So, all right, that's it. I'll see you in the next video.